Hello everyone, welcome back. This is our 11th lecture. Today we're going to be talking about interactions. It's also known as moderation in a lot of fields. So I'll be using both interchangeably. So what do we actually mean when it comes to an interaction? Well, it's when the relationship between a predictor and the outcome depends on a third variable. So the relationship between the predictor and the outcome depends on another variable. As I mentioned, it's also called moderation, and when it is called that, generally one of the variables is called the moderator and the other one's a predictor. So what does this look like? Well, for example, we have two variables, x1 and x2 category. The x1 variable is continuous, the x2 is just 0 or 1. And then we have our outcome y. Right here, this is an interaction between a continuous predictor, the x1, and a dichotomous moderator. And here you can see that the effect or the relationship between x1 and y is pretty small. The line is pretty flat when x2 is 0, but is a lot steeper. There's a lot stronger of a relationship when x2 cat is 1. So that means that the relationship between x1 and y depends on if you are 0 or 1 on x2. One thing that's important is either variable can be considered the predictor or the moderator. They're interchangeable. Generally, it actually depends on the research question or the story to be told. Often the moderator is this thing that is changing the relationship between the predictor of interest and your outcome. But the interpretation still means the exact same thing, whether you use one as a predictor and the other as the moderator or vice versa. But it can look very different. What's important to note is that it's still the same information, still the same interaction, but the story can be told very differently. For example, in this first plot on your left, when x1 is your predictor and x2 is your moderator, there's really no situation where the relationship is totally flat. There's some relationship between x1 and y, no matter what level you are in x2. So even if you're a 1 on x2, you have some of a relationship, there's some slope there. It just gets stronger and stronger as you go up. When you reverse those and you have x2 as your predictor and x1 as your moderator, there is a level where it doesn't look like x2 has any relationship with y. So when x1 is 1 or 2, it doesn't look like x2 has any relationship really that's really flat. It's not really until you get to 3, 4, 5, and 6 that you start to have much of a slope. So depending on which one we decide, it's going to change a little bit of how we tell the story. But again, it's the same information. It just depends on what your research question really is. So we're going to focus on two-way interactions. So two-way interactions is when two variables interact. So if there's a two-way interaction, that also means there's a 3, 4, 5-way. So there's many more complicated versions of an interaction. We're just going to focus on a two-way interaction in this class. When we're looking at two-way interactions, it can happen between two numeric variables. You can have a dichotomous variable and a numeric variable interacting. You can have two dichotomous variables interacting. You can have a multi-categorical variable and a numeric variable interacting. And you also can have two multi-categorical variables. All of these are going to be interpreted in very similar ways, but with some nuance. So here's some examples. You have the effect of the treatment on the outcome may depend on the sex of the participant. So depending on the levels of treatment, maybe we just have treatment and control. And then sex, depending on how we measure that, maybe male, female, and non-binary. So this could be an interaction between a dichotomous variable and a multi-categorical variable. You could also have the effect of smoking on heart condition may depend on the age of the individual. So if you're young, maybe smoking doesn't have as strong of an effect on your heart condition. But as you get older, maybe the effect of smoking gets worse and worse on your heart. Another example, the effect of education on income may depend on the economic climate. For example, getting an education when the economy is really good may have a really strong effect on your income, but maybe not so much when you're in a recession. So that's an example of a continuous variable, education, interacting with economic climate, which could be categorical, just good or bad or thriving or recession, something like that. But you could reverse all of these. And so you could say, for the first one, you could say the effect of sex on the outcome depends on which treatment they're getting. You could do that the same. The effect of age on heart condition may depend on whether you smoke. In the last one, you could say the economic climate on income may depend on education. And so each of these, they're telling a slightly different story depending on how we say it. But according to the model itself, it's still the same interaction. So the way that you tell the story isn't going to be dependent on the model itself. It's going to be based on your actual research questions. So let's talk about the general interpretation of the coefficients. So when we're actually running the model, we're still going to get coefficients out, but they're going to mean slightly different things when there's an interaction going on. So the interpretation here, doesn't matter if the variable is numeric or categorical, they're all going to mean ultimately the same thing. There's just going to be nuance in how we talk about it. So let's talk about each of these in turn. So first, when x2 is 0, the effect of x1 is that. It's 0.5. In other words, for a 1 unit increase in x1, there's a 0.5 increase in our outcome, y. That is only, though, when x2 is 0. Conversely, when x1 is 0, the effect of x2 is 2. In other words, for a 1 unit increase in x2, there's a 2 unit increase in y when x1 is 0. So let's go back to the full output, the full model equation, to understand what that 1.5 means. So ultimately, if we go forward a little bit, it is a difference in the slopes. So if x1 has this slope, and then when x2 is 1, and then when x2 is 2, x1 has this slope, the difference between those is 1.5. And then the difference between 2 and 3, so when x2 is 2, the slope for x1 is this. When it moves up to 3, it goes to there, and that slope is 1.5 units higher than when it was 2. Again, if we come back to this full model output, to understand the effect of x1 as a whole, we need to find all the places where x1 is in this equation. So it's not in that first number, 2, plus 0.5 x1. Okay, we have that one, so we want to hold on to 0.5 x1. The next thing, plus 2x2, there's no x1 there, so we can drop that. And then this last one, 1.5 x1, x2, there is an x1 there, so we're going to hold on to that. So what the effect of x1 ends up being is everything that's tied to x1, but we just drop the x1. There's a reason why, and it's due to calculus, why we do that. We're going to talk about that more in nonlinear relationships, but right here, just note that the effect of x1 is 0.5 plus 1.5 times x2. So all we did was drop x1 from the places that we pulled it from. What that means is that the effect of x1 is 0.5 plus 1.5 x2, which means that it depends on the level of x2. If x2 is 0, then we just plug in a 0 where that x2 is, and we get 0.5 plus 1.5 times 0, which is 0.5. Like we mentioned before, the effect of x1 when x2 is 0 is just 0.5. So what's the effect of x1 when x2 is 1? Well, we plug in a 1 where the x2 is, and we have 0.5 plus 1.5 times 1, which is just 1.5. So we add that all together, so it's 2. So when x1 or x2 is 1, the effect of x1 is 2. What about when x2 is 2? Well, we plug in a 2 there, and we get 2 times 1.5, which is 3, plus a 0.5, so we get 3.5. So the effect of x1 when x2 is 2 is 3.5. So how do we interpret that in context? Well, we'd say for a 1 unit increase in x1, there's a 3.5 unit increase in the outcome, y, when x2 is equal to 2. Hopefully this is starting to make sense. The same idea actually holds for x2. So the effect of x2 is 2 plus 1.5 times x1. In other words, the effect of x2 depends on the level of x1. When x1 is 0, the effect of x2 is just 2, which means for a 1 unit increase in x2, there's a 2 unit increase in y. What about when x1 is 1? Well, the effect of x2 becomes 2 plus 1.5 times 1, which is 3.5 for the whole thing. So when x1 is 1, the effect of x2 is 3.5. In other words, for a 1 unit increase in x2, we see a 3.5 unit increase in y when x equals 1. So this holds exactly the same regardless of whenever your variables are numeric or dichotomous. It's just going to change how you talk about the variables when you're interpreting them. So again, the intercept is always going to be when all variables are 0. So when x1 and d1 are 0, that is the average of y. So in this case, 2. This is the conditional effect of x1 when d1 equals 0. So terminology-wise, that's called a conditional effect. That's different than a main effect, which we learned about in ANOVA. This is a conditional effect, which means it's the effect conditional on when d1 equals 0. Similarly, the 2 is the conditional effect of d1 when x1 equals 0. And then this quantifies how much the conditional effect of x1 changes as d1 changes by 1 unit. Or in other words, it's a difference in the slopes. And then you have the cross product, the x1 times d1, which is the interaction variable itself. So consider an example where we have the hospital data, which has safety violations, that's the outcome. We have how exhausted they are, times, which is in our code, symbolizing an interaction, times sex, which in this data is just male or female. And we get the summary of that. And what we end up getting are these coefficients. So for exhaust, we have 0.136. For sex male, we have negative 0.459. And then the interaction, where you have the colon between them, exhaust colon sex male, we have 0.318. And notably, the interaction is significant, which means we're going to hold on to it. We're going to interpret the interaction. If it's not significant and it's not a major player in our research question, we'll often just drop it and talk about just the main effects of exhaust and sex male without the interaction in there. So again, the intercept here is the average Y value when all variables are 0. So when there's no exhaustion, the sex is a female, our average Y is going to be 3.3. So for a female that is not exhausted at all, their average safety violations is 3.3. The conditional effect of X1 when D1 equals 0 is exhaust. So when we're female, the effect of exhaust is 0.136. In other words, for a 1 unit increase in exhaust when we're female, which is the exact same thing as saying when D1 or the sex variable equals 0. So when we're female, for a 1 unit increase in exhaust, we expect a 0.136 unit increase in safety protocol violations. Similarly, the sex male is the conditional effect of D1 when X1 equals 0. So when you're not exhausted at all, in other words, exhaust is 0, then males commit 0.459 safety protocols less than females do. So when there's no exhaustion, males, although it's not significant, are slightly lower than females in how many safety protocol violations they have. And then we have this 0.318. This quantifies how much the conditional effect of X1 changes as D1 changes by 1 unit. When D1 changes by 1 unit, that goes from female to male. So let's talk about exactly what that means. Again, the cross product is where there's the colon between them. So what exactly does a 0.3186 mean? Well, it means when we're male, so we plug in a 1 for sex, and we're looking at the equation, we're going to say the effective exhaust when we're male is the 0.136 plus the 0.318. In other words, the effective exhaust when you're a female is just 0.136, but when you're male, it's 0.136 plus 0.318. The reason why is we have to look at everywhere where exhaust is. We want to understand what the effective exhaust is. We have to look everywhere where it's at. We find it in that line right below the intercept. So 0.136, we hold on to that one. And then we also find it in the 0.318 line. So if we're female, then we plug in a 0 for the sex male, and that one drops the 0.318. So we're just left with a 0.136 for exhaust. But when we're male, we plug in a 1, and so now we have exhaust with the 0.1367 plus 0.318. So when we're male, the effective exhaustion is a lot bigger. It is 0.45-ish. So if you're female, the effective exhaust is 0.136. When you're male, the effective exhaust is 0.45, roughly. So it's important to note that the way we are interpreting that made it so we could say when you're male or when you're female, these are the effective exhausts. And that's because we had a dichotomous variable in there that when it's 0, it meant female. When it was 1, it meant male. When you have two numeric variables, that's not the case. The interaction still means the same thing. It's the difference in slopes. But now we can't say when x2 is 0, We can't say that that means female or something like that. Instead, it just means when x2 is 0. Often when we're interpreting those, we have to plug in values of the moderator. So in this case, like x2, that makes sense. So we could try out 1, we could try out 3, we could try out 5, and see what the slope looks like in each of those situations. When it's two dichotomous variables, this is often interpreted, you see this a lot in like ANOVA situations. And this one is actually often the simplest to interpret with a figure. We're going to show a lot of figures, but often this one is fairly straightforward to interpret as a figure. Another way to talk about this one, the dichotomous variables, is what's called difference in differences. So we're saying the difference between the levels of D1 depends on the difference in D2. So it's often called difference in differences analysis. But like I was hinting at, my recommendation is to always use a figure. And as Severus Snape always says, always. You want to just always use a figure. So for example, when we visualize an interaction between two numeric variables, we need to group one of them into some groups to better see it. It's hard to see it when we just leave both of them as continuous. So whichever one we're considering as a moderator, we can group those into categories. In this case, we grouped all the lower values, the middle values, and the high values together. And we do that not for the interaction itself in the model, but just for the figure. Like I'll mention later on, you do not need to categorize anything. You can have an interaction between two numeric variables just fine. But to visualize it, it's helpful if you dichotomize one of them. And in this case, we'd be able to say if you have a really high score on x2, then it looks like the relationship between x1 and y is bigger. There's a stronger relationship, there's a bigger slope. It doesn't look like there's much of a difference if you're in the middle or low end on x2, where the slope of x1 is roughly the same. When x2 is already just dichotomous anyway, you just use that as a moderator and you look at the relationship between the two like we have here. And in this case, we can see that when x2 is 1, there's a bigger slope than when it's 0. When we visualize an interaction with a numeric variable and a multi-categorical variable, we can use the multi-categorical variable as a grouping variable. So in this case, if we're in group 1, 2, or 3, it looks like if we're in group 2, we have the biggest slope, group 1 or group 3, we have somewhere in the middle, and then group 1, we have the smallest slope. Now, I would definitely say that there's probably not a significant difference in the slopes between group 1 and group 3 here for x1 on y. I think the easiest one is when you have two dichotomous variables. You can just use either one of them as the grouping variable and the other one as your predictor. And you'll often see it shown this way where you have an error bar and it shows the slope from going from 0 to 1 for when your x2 category is 0, and then from 0 to 1 when your x2 category is 1.